Let's go back to what we were doing. Remember the situation we have. We have the second moment probability measure on a group. We have a unitary action. We have a harmonic co-cycle. And we were investigating what happens when you take the co-cycle tensor with itself, so inside the Hilbert-Schmidt space. So let me do the computation again, because last time we kind of started playing around with it. We kind of got the wrong direction. I explained what was wrong about it, but let's try to see if we can do it right this time. Well, so I want to look at what happens to an object of this type, Cxy, tensor with itself. So you remember this notation where I take the power tensor with itself, right? So this is this, by definition, is exactly equal to Cx plus x acting on y on C of y. This whole vector, this is a vector in the Hilbert space, and I can take its tensor with itself and look at that as a vector in the Hilbert-Schmidt, as an operator in the Hilbert-Schmidt space, right? And this guy, we can use the linearity of tensors, which I only claim is true and did not prove, but it's a simple exercise, to show that, to compute what it is. So I get C of x with itself, right? Cx, right? That's one of them. Then I get, let me do the last term first, because again, the cross terms will be less important. I also get xcy with itself. So I get x dot cy. All of this cross 2. Okay.
Yes, x cy. Can pull out the x.
You can pull out the x in a minute, but at the moment, what this says is a certain vector, which is called x dot cy. Right? This is some vector cross with itself. And then I have two cross terms, right? The cross terms are cx cross xcy. This I cannot write as a tensor with something with itself. It's a cross term. That's why I'm calling it a cross term. And the second cross term, which I'll write under it because it's basically similar, is xcy cross c of x. Formally, these are not the same object, although you can want them to be the same object in a certain sense, but they're not. Okay. Tensors are not commutable. It's completely different if you tensor two vectors in RD, right? I mean, it gives you the different matrix. Right? I mean, a tensor is different. And, you know, you take two vectors in RD and you take their tensors, then you get the matrix. Well, I think just do the definition. That's why Hilbert-Schmidt is exactly the generalization of matrices.
Simply just one is on the span of the right coordinate and one is on the other one.
I mean, it's just a matrix multiplication, but what I have started to call the podcast multiplication, because it's how you taught multiplication of different size matrices, right? For me, this is like some kind. What is this? So this is a tensor product. This is actually a tensor product. If you take matrices of correct sizes, then they're actually, one is the linear functional, and well, so you can define tensors. But if you but kind of the matrix product, the square matrices have like a maybe more structure to it in the sense of its composition of linear maps. So I kind of, these things are kind of separate from me. I mean, they happen to collapse to the same, algorithm if you, define it in a certain way. But that's just the way we like how the computer computes the new object, not really what it is. So matrices you can
it's like creation. You kind of what they did, taking the entries of A.
okay, you can compute
I
well.
would,
You can take two matrices and you can have different sizes and you can tend them. So it's possible, right? And this acts on some space. It's exactly this. Okay, and then it's completely not commutative. So it lives in different worlds. Even like I mean, vectors are coming from different spaces, right? So just remember what this thing is. It's projecting onto a certain direction, onto this direction, right? And scaling by the projection of this vector. So I mean, so it's completely living it's living in the space where this second vector lives, and it could be a different space. But okay, that's mumbo jumbo. These are the cross terms that we get. Okay, so I have two cross terms. Now let me just write one more term for this guy. So we'll do it in a different color maybe. This guy exactly is x minus 1 of the operator cy squared, right? So this is now composition of operators. You have to understand, you have to convince yourself that, first of all, these two operators are the same operator. Second, you have to convince yourself that well, once you convince that they're the same operator, you prove that this is actually in the Hilbert-Schmidt space. But conjugation by a unitary operator still lives in the Hilbert-Schmidt space. Okay. Just compose a unitary operator with a Hilbert-Schmidt operator, you don't necessarily get the Hilbert-Schmidt operator. Okay, you don't necessarily get the Hilbert-Schmidt. I think.
maybe you always get a complex operator, right?
Well, we need to find the Hilbert-Schmidt norm. So you have to ask yourself, does the norm? So composition on the first composing with a unitary operator, then taking a Hilbert-Schmidt will be a Hilbert-Schmidt because it will just sum the norm right on a different orthogonal basis.
Yeah.
But post composing with a unitary, no, but this will preserve the norm. So it is. So composition is it. I mean, just because the norm converges.
We leave that only the first one, it doesn't matter. Then in conjugation.
Oh yeah, right. No, but it does. It works. So okay, so I take it back. Composing with the Hilbert-Schmidt operator is a unitary with the Hilbert-Schmidt is a.
But conjugation.
Hilbert-Schmidt.
It's not an action.
Well, it is an action. It's a right action.
Okay, I'm gonna say stuff.
Okay, but this is the equality that you have to. Yeah, that's actually a good point. That composing is a Hilbert-Schmidt. Okay, so we have this. What happens? What happens if I now? So C is mu harmonic. So if I average over Y or average over X, okay? If I average over Y, you see the average gets pulled in because of the linearity, and it gets pulled into the operator. So these become 0. If I average over X, same thing. If I average over X, then well, you have to be careful. Why, when I average over X, these become 0 because I have an X here and an X here.
Can we maybe cancel it? Or?
Well, so we can cancel it, right? So we, should be able to cancel it, but why did I not write it? No. Yeah, so you have to be careful. You have to be careful if you want to cancel it. It's going to be a bit more complicated. You can pull the. Okay, it's not clear that if I average over X, this is going to become 0. It's only clear if I average over Y that this is 0. Now, the thing is that I can average over Y, not just with respect to mu, but also with respect to mu to the T. Also with respect to the T steps, right? Because harmonic stays harmonic. You take, okay? So what we're going to do is let's define AT. Yesterday I called this A tilde, but today I'm going to define AT. This is going to be the sum over all x's, probability that xt is equal to x, which is the same as for those of you who prefer convolutions, it's mu to the t x, right? times C of X with itself. This is a vector in the Hilbert-Schmidt space. This is a convex combination of vectors, okay? You have to make sure it converges if you take mu of infinite support, but it will if you take the correct moment conditions, which is only first moment, right? Because these guys are Lipschitz, okay? So this will converge. Sorry, you need mu of second moment for this to converge. Why? This is a square. This is a square, okay? But we took mu of second moment, okay? So this is a square, so this converges even if I take mu of infinite support. But that's not going to be important. We will have a choice of mu at the end of the day, so I could have worked with finite. Okay, now this specific with this definition, okay, I want you to notice what happens when I average this over y. So the sum over all y, probability xt is equal to y of c of x cross x dot c of y. What is this? This average can come inside, and this is a mu harmonic cocycle, and averaging a mu harmonic cocycle around the origin gives you the value of the origin, which is 0. So this is 0, and the same would be if, of course, if I did this just a different, and this uses the fact that 0 tensor with acting on 0 with x is 0, and 0 tensor with anything is 0. Okay, so that's the formal. But then we can write. So write xt plus 1 equal to x1 times xt tilde, where xt tilde is independent of x1 and has law u to the t. Right? You can do that. What is xt tilde? Just define it.
x1 inverse xt plus xt.
It is, right? Just shifting the random walk. And we know that this works, right? So, okay. Or if you want, you take this to be a product of t independent mu distributed things. You take this one to be a mu distributed thing. They're independent by definition. So, okay, so you have to convince yourself that these two things, that this thing is independent of x1 like this, right? Because it looks at the different steps. Okay? If we write it this way, then what do we get? We get that at plus 1 is equal to, right? Well, what is it equal to? It's equal to, so I'm doing that split, right? So I'm averaging over, yeah, so it's equal to the following. First, let's do the average, okay? So I have sum over x and y. I have the probability that x1 is equal to x, and they're independent, so I can take the product of the probability that y, that x tilde t is equal to y, right? I can sum these over, and this is times c of x, y, inner product, inner product, tensor product. Okay?
And usually in Markov chain, right? x1, x2, x3 are not
the steps are independent. The increments are independent. But in a general Markov chain, they don't have names. In a random walk on a group, they have names. You're just multiplying by independent. So, think of just a random walk on a graph. I have to tell you, you could have a random walk on a Schreier graph, right? Schreier graph will have labels. Okay, so you can think of a graph where every vertex, the outgoing edges from the vertex, or all the edges, they have numbers written on, or letters. And you have a direction, so every time you're at the vertex, you choose one of the letters uniformly and go. So if I give you a specific, if all the vertices have the same letters on them, which is just saying Schreier graph, basically, then what you do is you tell me, you give me a list of independent letters, and this tells me how I walk in the graph. Okay, so it's more general than a K graph. You can do it with a Schreier graph, but it has to have some structure. If it's just a general graph, I need to know where I am to understand how to proceed with the instructions. And the word I'm telling you, I can't just specify ahead of time, follow these letters, because it doesn't make sense if I'm at a certain stage. What is the left edge? What is the right edge? What is the red edge? What is the blue edge? You have to see all the colors or something like that.
There are like no random increments. Just at any position, you look and what should I do now?
The next step depends on the current position. The description of the next step depends on the current position. If you have a situation where the description is independent of the position, then basically you have a Schreier graph. In the Schreier graph, you can give a list of instructions ahead of time. So you have one machine, it just generates infinitely many independent elements from a group. Right? And this gives you the instructions of how to walk. So the guy starts here, and he knows where to go. I'm not going to say guy. I'm going to say guy.
Guy is the name, or guy is
She said, why do you always say guy? Say vertex, say
student of the first year also like when Makievich says like, you take this guy and he tells us about numbers.
Yes, because I have a personal relationship. I'm not like that guy, maybe it's a girl.
Yeah, now it's 2024, so now
I told her that I'm too old.
We can't assume their gender.
No, I mean, I understand. I'm not making fun of it, but it's a habit that it's hard to get rid of. Okay, so I'm going to rewrite that. So AT, what is it? It's the sum over all x and y. I didn't write it down there. Probability x1 is x. What I did here is just the convolution, right? And now what I just erased tells me how to compute this. Now everything is nice and interchangeable, right? These are sums of probabilities.
So it's CX1.
I wrote CX1.
On the definition.
No. This is when I do t plus 1, I change it into a convolution of 1 and t. So this became a convolution. It became x times y. When you're averaging, what is it? This has distribution of x1. This has distribution of xt, right? And they're independent, and you take their product, so that has distribution of xt plus 1. Right? This is how to think of. Somebody asked, what is a convolution? I said convolution is just taking two random objects and multiplying them and getting the law of the new random. That's good. Okay, so that's what I'm doing. Just splitting the convolution up into 2 steps. Okay, and now when I just look at the sum over y, the inner sum, remember the cross terms disappear. So you see, I don't do over x, I do over y. You have to be careful not to average over x, because you have the x acting in the other coordinate, and then it's a complication. They conspire together. But the y is standing alone, independent. I can sum over all the y's, average over them, I get 0. So the cross terms disappear. So what am I left with? Remember, I was left with cx with itself, averaged over x1, right? So cx with itself, averaged over x1, this is a1. Right, you agree?
With the xt,
xt tilde?
No, what has the long
xt tilde.
Oh, right.
It has the t steps. Okay. So from this, I get two non-cross terms, right? So I get cx with itself, averaged over x1. This is a1, right? By definition. Plus, I get, let me really spell it out for you. Probability. Now I can change x tilde t to xt, right? Because they have the same distribution. So I can just write probability of xt. I don't need tildes anymore, right? The tildes were just to make them independent in the same space. And once I put it by alone, the probability that xt tilde is equal to something is the same as the probability that xt is equal to something.
Why
is it 80 plus 1?
Oh, you just split it in.
I split it into 2 things. I did the convolution. The first term, the cross terms disappear. The first term becomes a1. And the second term, I'm writing it down. It's this sum, right? x minus 1 c of y with itself. Now, if this sum was inside, it would be exactly a t. Right? If the sum was inside. But that's fine, because I'm taking a linear combination of operators. This is a linear operator, bring it outside.
The sum of x. Yeah. Who is it?
Yes, there is a sum of x. Right. Okay? So this is what you get. So I bring the sum of the y inside, and what I get is a1 plus some operator t acting on at. So who is the operator t? You can tell me. Where? Okay, so I get this equation.
Can you explain again this step?
I didn't write what t is. Let me write what t is. Where t of an operator a is defined to be, so t is what? T is going to be a bounded operator on Hilbert-Schmidt space. Going to eat a Hilbert-Schmidt operator and spit out a Hilbert-Schmidt operator. Okay? And it's defined to be that when it eats a, it gives me the sum over all x's, mu of x, conjugation of a with x. It's a convex combination of Hilbert-Schmidt operators, which gives another Hilbert-Schmidt operator. Okay?
You enter the scalars inside the x, right?
No scalars. What scalars?
The p, x, t.
Oh, this.
Yeah.
Yeah.
You enter them inside the.
This comes in here.
And the y.
This sum.
And this is not zero.
This is. You have this. What is this sum together? What is the blue sum? The blue sum is exactly at. By definition, I defined at to be this sum. Just this is y now and not x. Right? The average over tensor with itself, C tensor with itself, according to the mu t. Okay, so that's exactly, so inside I have an at. Outside that conjugation, and I'm summing over the, averaging over the conjugation. So it's that averaging over conjugation is a linear operator. It's a linear operator. And I call this linear operator t. Okay, so we have an equation, right? We have an equation. T is a bounded operator. Well, you have to convince yourself that T is a linear operator. That's easy to see. Okay, so exercise. Show that T is a bounded linear operator. Okay, linear operator on what? On Hilbert-Schmidt space. So T is already on level 2. Hilbert-Schmidt was level 1, Hilbert space was level 0, level 1, level 2. Okay, don't be confused where these things live. So T lives on level 2. It's a linear operator. It's bounded. You have to check linearity. You have to check boundedness. I mean, you have to check operator norm. And the operator norm of T. So what is this operator norm? This is from Hilbert-Schmidt to Hilbert-Schmidt. Okay? So the operator norm, you activate it on a unit Hilbert-Schmidt vector. Okay? You get what you get. And this is less than or equal to 1. So it's a contraction on the Hilbert-Schmidt space. Okay? But it doesn't matter because Hilbert-Schmidt is a Hilbert space, right? It's a Hilbert space. Oh, great. Okay, so this is the exercise. Show that it's a contraction. And show that
you get an operator and you get plug in an operator and you get an operator, right?
Yeah.
It's just another Hilbert space. So,
out zoom in.
Okay. So we have our Hilbert-Schmidt operator, and we have our contraction, and we have our equation, right? We have this equation. So from this equation, what do we get? We get that AT is just, I mean, it's A1 plus T acting on AT minus 1. And that's A1 plus T acting on AT minus 2. And so at the end of the day, what do you get? You just get that this is J goes from 0 to T minus 1, T to the J acting on A1. A1 is now going to be a fixed vector in the Hilbert-Schmidt space. Okay?
Yeah, T is also variant. I mean, if you conjugate the operator A inside T, it stays the.
This is coming with the weights given by the weight. Good. By the way, T is also self-adjoint, right? I will say T is self-adjoint. Okay. So we have this equation, and we have the T is self-adjoint contraction. So what do we know? Therefore, by Neumann quadratic theorem. What? You just check what it does to reserves in a It's because the conjugation is a unitary action in the Hilbert-Schmidt space. Okay. So unitary actions preserved from its combinations of them. Okay. Good. By the phenomenologic theorem, what we have AT divided by T. What is this? This is just the Birkhoff sum, right? The average, right? So we know that this converges. Where is this converging? In what space? No. This is a vector in Hilbert-Schmidt. So this is converging inside the Hilbert-Schmidt space. Okay? Hilbert-Schmidt norm convergence. Okay? 2. That's what the phenomenologic theorem says. If you have something that you can write as a self-adjoint contraction, it's a Birkhoff sum, right? When you take the average divided by T, it converges. Where does it converge to? To pi of A1, right? That's the vector that you're averaging over, pi of A1, where pi of A1, or where pi from to itself, right, is the orthogonal projection onto T invariant vectors. Right, T invariant Hilbert-Schmidt operators, just to not be confused with vectors in the original space. Okay, so all Hilbert-Schmidt, you take the collection of all possible things that are invariant to this operation T, to this averaging operation, and project this. Okay, specifically what? Specifically, pi of A1 is T invariant. Okay, let us call this guy L. Well, okay, not L. Sorry, yeah, let's call it L is limit. L is limit. Okay, and we know this limit exists. It's a Hilbert-Schmidt operator. Everything is well defined. It could be 0. Not say that you have to necessarily have the invariant vectors which are non-zero. It could be that the whole space is just a 0 vector, right? So we will have to deal with that case. Okay. Yes, that's the case. Okay. You know, that was the reminder. I want to remind you about what we did with the variance. When we were computing Ex C XTV squared, right? We had this function, we took its second moment, right? When we were computing this thing, right? We rewrote this as what? We rewrote this as C XT tensor with itself, inner product with V tensor with itself. Right? This thing is exactly the square. That's the trick.
With some
No. This
yeah.
is CXTV, VCXT, and that's exactly what. Yeah. That's the variance. Wait, you'll see how you get the variance in a minute. See how you get the variance in a minute. Okay. Now, I can rewrite this just slightly. Instead of taking expectation starting from X, I'm taking expectation starting from 1. So when I don't write anything, I mean starting from 1. But that just means do X times a random walk starting from 1. Instead of starting from X and doing a random walk, right? So this could be written as the following C X XT tensor with itself, V tensor with itself. And now a similar computation to before, we pull out the x's. How do we pull out the x's? I have Cx plus X acting on CXT tensor with itself. I just said that the distribution of xt under this measure is the same as the distribution of x times xt under this measure. Same thing. Just independent elements to the next. Just wrote. It's just that under this measure, x0 is x with probability 1. So you can just write it down.
What was the x in the first, like in the beginning of it?
Any x. I'm just doing it for any x. Start at any x. Okay. Now I just want to show you how the x doesn't really matter. I could have just said x equals 1 and didn't do it.
This is the reduction to x equals 1.
Well, in a sense, yes. Okay. Now what happens when I open the this linearly, right? So what do I get here? I get cross terms plus so I get CX2 plus X acting on the Hilbert-Schmidt operator, so I can do it this way, right? That's the same as the computation as before. Plus 2 cross terms, right? Plus CX cross X acting on CXT plus CXT, X acting on CXT cross CX. Now, remember, this is everything here is Hilbert-Schmidt, and it's inner product with the Hilbert-Schmidt BV, V cross V, right? So we'll soon get to the inner product, but let's look at the cross terms. When I take the expectation over XP, I can bring it into this average just over these, right? Because everything else is fixed. V, X, everything else is fixed, right? So the cross terms disappear, just as before. The cross terms disappear when I take the average, right? Okay. What am I left with? I'm left with this inner product V, this inner product. But this is a unitary action. The conjugation is a unitary action. We said it's a unitary action. Okay? So I can You agree I can put it to the other side by x minus 1? So what I get from this computation, and if you're not convinced, you should check it, verify it for yourself, because it's exactly the same computation that we did before, is that this thing is equal to Cx V inner product squared. This is what? This is Cx cross Cx, inner product V cross V, right? And there's no expectation anymore because there's no randomness. Okay, just expectation over constant. Plus, cross terms die, plus I'm moving the conjugation by x to the other side because it's a unitary action. So plus the expectation of what? Of C xt cross with itself, inner product x minus 1 v cross v x. Okay, this was by moving. Then I have to take inner product. This is Hilbert-Schmidt inner product. Okay, remember this is Hilbert-Schmidt inner product. Can move the x to the other side because it's a unitary action. Okay, but what is expectation over Cxt squared? Now you see this is left alone. I can bring the expectation into the inner product, right? It's just a linear combination, convex combination of these numbers. But then when I bring in the convex combination into the first term, I exactly get 18. This is exactly 18, right? Averaging over all the xt's of this tensor with itself. So this is equal to, now what is this? C of x is exactly the expectation of C of xt. Or C of x in the product V is exactly, so this is exactly the expectation under x of Cxt inner product V with the absolute value squared outside. Right? Because when I do this average, I get C of x under starting from x. Okay? Plus AT inner product x minus 1 v cross x, v cross v x. Inner product in the Hilbert-Schmidt space. This is why I defined AT. This is why I defined it. Okay? In fact, I get to AT by looking at the variance. So now take the difference between two sides, take the difference between this and this. Is exactly the variance. Expectation of the square minus the square of the expectation. That's exactly the variance of our harmonic function.
It's a random thing. What?
There's no randomness. HT again today was defined to be the average over the randomness. AT is the sum over x, mu t of x, C of x cross C of x. Okay? If I bring this average, I write this out as a specific average over x, right? Then I have C of x plus 0, I bring it into the first coordinate, I get it. Okay? It's really just a game of summing things and using linear. Really just a game of summing.
So 80 is random.
80 is not random. Yesterday it was random and I had 80 theta. I said today 80 is what yesterday was 80. Okay? But anyway, we did it early. Okay? Just because I don't need to tilde it. No, that's why. The way I got to 80 was by looking at the variance. Then I decided, okay, let's look at this object as a fixed object and see what happens. Okay, so what we got is that the variance of, remember what this function was, hv xt. This is the inner product of c with v. It's just this function, right? So the variance of h starting at x, meaning you take the expectation squared minus the square of the expectation, is exactly equal to, this is an identity, is exactly equal to the inner product of this AT guy with x, v cross v, x minus 1. I did it opposite, x minus 1, x, in the Hilbert-Schmidt. This is the important identity. This is the definition of AT. And
one small thing. Why did we change the order of x inverse x? Because outside is
when I had, so what did I have? I actually had here x conjugating this guy. This is a fixed. Now this is before I take expectation. X is inside, and it was inner product with v cross v. Okay.
so
This is a unitary. This action of conjugating something with a fixed x is a unitary operator. So I conjugate both of them by x to the -1. Here it disappears. Here it becomes x minus 1. Okay. So that's how I move it to the other side. Okay, good. So I have those three purple squares I can erase here. It's really, really just a computation, and you just have to get rid of doing basically averages inside Hilbert spaces. Okay. So it's just not really complicated. You discover all of a sudden. So I mean, you compute your variance. You get that it's some AT, product to some AT. Then you start analyzing your AT. You realize that it's a Birkhoff sum. Birkhoff sum I can take care of it. Here it converges to some limiting guy, which I call L. Okay. So now we have to analyze L. What happens if L is 0? Could be 0. That vector is 0, right? If L is 0, what did I get?
Complement.
Then this variance. By the way, the convergence of this thing, right, does not depend on x. You see? AT over T is converging to L no matter what x. So all the variances converges to the same thing. X comes in on the second coordinate. There's also a choice of V that you can make, right? You can do this for any V. Okay? So for any x, and for any V, the variance starting in x of HV xt, all of this divided by t, converges to, as t goes to infinity, 0 inner product with xv, or let me write it explicitly, converges to L, because this is weak convergence. And it's weaker than norm convergence, right? AT over T is converging in the norm to L. So this converges to L. This is not just for case 1. This is for all the cases. It converges to L x minus 1 V cross V x. Okay? In case 1, this is 0. This was one of the cases of Ozawa's theorem, where I told you have a sublinear Lipschitz harmonic function form, right? One of them is not going to be non-constant. This is the case that in polynomial growth we're going to say is impossible. Okay.
Now it's not 0, then we take the extra variant.
Yes. So now we'll have. So this is the probability until now. Then we have the algebra. Then we have the algebra. Okay. So let's see what happens in the other cases. So case 2 is L is a non-zero invariant vector. T invariant, right? This is not a G invariant vector. It's invariant to some specific operator T. Okay.
That just means that T sends the spin.
Yes. T of L is L. Okay. L is some vector that's preserved by T. Okay. Now, my claim is, which I will prove maybe later, or give you as an exercise. It's not a very difficult one. Okay, so now we're in case 2. This was case 1. Claim T TL is L implies XL x minus 1. This is the G action, is L for every x. T invariant implies G invariant. Why? For this specific T. T is the average of a random walk, and the random walk is generated. This is very important. This is a convexity matter. But this claim comes from convexity of the unit ball in Hilbert-Schmidt, or convexity of balls in Hilbert spaces. Balls are convex. You cannot take the average of vectors with the same norm and still get something on the boundary, unless, right? If you take average of vectors of the same norm, then it goes into the ball, doesn't stay on the boundary, right? You cannot take averages of vectors and get something stays on the boundary, unless, of course, you took the averages of all the averages were the same. Okay, T is an average of different things, and it's staying the same. It's staying on the boundary. It's staying the same. So it has to be that all of them were just basically the same. So this means the support of mu acts trivially, but if the support of mu acts trivially, then everything acts trivially because mu is general. Okay, so that's an exercise, but we'll solve it together. But maybe not today. Okay, but now you can believe me. Any T invariant vector is a G invariant vector. This is an important thing. Okay, so now we have a non-zero G invariant vector. Right? What does this mean? We already saw that the eigenspaces for this thing, or for the symmetrization of this thing, are finite dimensional invariant subspaces. So there exists a V inside now level. We go back down to level 0. The whole idea to go up to Hilbert-Schmidt, this is the ingenious idea. I mean, it's a simple idea, but it was like unnoticed by everyone. When he found this, it was surprise, kind of, to me. Kind of kicked myself for not really noticing this. But you go up to Hilbert-Schmidt, it tells you something about the variance, then you come back down to level 0, and there exists a V of finite dimension, but non-trivial, okay? And it's G invariant. Right, we have a finite dimensional G invariant vector. This, I claim, is what I was looking for all along. This, I claim, is what I was looking for all along. Why is this what I was looking for all along? Well, now I have to split again into two cases. Okay? So we define N with all X in G, such that for every V in my specific vector space V, XV is equal to. This is the kernel of the action of V. So G is now acting on a finite dimensional space. So it's acting on V. And this is the kernel of this action. Right? It's easy to see that N is a normal subgroup. It's a kernel of an action. G, what does this mean? This means that there is a homomorphism from G into the unitary operators on V, which is a finite dimensional space. And this is just the kernel of this action. Okay, kernel of a homomorphism is a normal subgroup. Okay, I'll check it right. Okay, so this means that G modulo N is isomorphic to the image of the homomorphism. But the homomorphism, where does it live? It lives inside unitary operators on a finite dimensional space, right? So this is isomorphic to some, say, G hat. Where is G hat? Which is a subgroup of unitary operators on V. But unitary operators on V, right? I could replace the homomorphism. These are isomorphic to unitary operators on C to the D of some D, right? I could just change V to be, it's a finite dimensional space. So we can imagine now isomorphic to G hat, say, which is a subgroup of U C to the D, which I can write UDC. This is D by D unitary matrices over C. Okay, I'm going to erase this line. This is just explaining why. So G mod n is isomorphic to a subgroup of D by D matrices. This is D by D matrices, unitary matrices. Unitary in the matrix sense. Complex conjugate transpose is inverse, right? Okay, so we have a linear algebra problem now. Now it's a linear algebra problem.
What do you want to show?
Well, we want to show that there is a homomorphism up to a finite index subgroup. There is a homomorphism. Well, okay, we want to show that G is virtually G has polynomial growth virtually impotent, but we'll see what is enough. Let's see what mileage we can get just from this fact. Some of the things I'm going to leave unproven because I do want in the rest of the course to get to at least next week. I want to start doing some bounded stuff, bound harmonic functions, or maybe unbounded, but like more interesting, like not just the Gromov's theorem. So this is basically going to be almost the end of Gromov's theorem. But we should take a break. Okay, so let's take a break and then we explore the algebraic possibilities. I want to finish basically most of the steps of Gromov's theorem today, except maybe the introduction.
Still the group notion.
Yeah.
And
Identical. Okay. So now, yeah. So now we have case 2, right? Where the invariant vector is, we have a non-zero vector. We used it to get a non-trivial finite dimensional subspace. This was the whole purpose. Now we can forget about the invariant vectors and we can just focus on the finite dimensional invariant subspace. What we have is a quotient of unitary matrices. That's all we're interested in. Okay. Now there are 2 cases. Case 1a, which is a simple case. Case 2a. Okay. This is if the index of n in G is a finite group. Could happen, right? It could in fact be that n is all of G. I never said that the action on this invariant space is not a trivial action. It could be. It could happen with G absolute, or just up to finite index actually. But then let's check. Let's check what is HV of xy. Okay, what is HV of xy in this case? Sorry, for xy and n. Xy. I take 2 guys in n, and I check what is HV of xy. So this is C xy in a product with V, right? That's the definition of HV. Okay, and C in a product with C of xy is C of x plus x acting on C of y in a product with V, right? We use the cosine.
from the specific field.
Yes. Xy in n and V in V. Thank you. This is very important. Okay. Remember that we have a V, so that it's non-zero. So that this inner product is non-zero. Yes, not exactly. We can, yeah. So I'll need to say that one of these is non-zero. Okay, but we'll say that in a bit. Okay. So what is this? Now I can split this. It's C of x in a product with V. What is C of x in a product with V? That's just HV of x, right? Plus, I move the x to the other side. How can I move it to the other side? It's a unitary. So if x is in n, what happened to this V? Nothing. So as long as x is in n, in fact, I didn't need y to be in it. I only needed x to be in n. Okay, this becomes HV of x plus HV of y. Okay, so H is a homomorphism. H is a homomorphism. Okay, now you can say maybe H is 0. Maybe H is 0, so you have to be careful. So the reason that one of these H's is not 0, right? Because, so recall, there exists a V, non-zero V in V, such that LV is not 0, where L was the invariant vector. right? This came out from when we did the finite dimensional subspace, we also made sure that we had vectors there. They were basically eigenvectors of the symmetrization, right? So one of them had to be non-zero. And what does this mean? This means that the projection of A1, right, acting on V is non-zero, okay? In fact, the projection of A1 V inner product with V is non-zero. Okay, but what is the projection? Yeah, so this is the what did I want? Yeah.
We know
What?
if V is not zero and LV is not zero, that might be that LVV is zero.
No, if
Then we can,
yeah. 1 second. So I want from this. All I wanted to claim is that oh, LV is not zero. But what is this? This is a Hilbert-Schmidt acting on a vector. Okay, so it's the limit as t goes to infinity of what? At divided by t acting on this vector. Because L is this thing. Okay, I have to remember what this is. Now, what is At acting by divided by t? So it's the limit as t goes to infinity, 1 over t. What is At? It's the summing over all x, mu t x, right? This is C with itself, right? C with itself. Acting on V. Now, what is something acting on V? Right? It's you take V inner product with this Cx and go in the direction of Cx.
Why is this H field why not take the X minus
What?
the less well?
I said when V comes from my invariant space, and I was assuming that X is from N, so X trivial. Okay? The restriction of H to N is a homomorphism. It's true that it's not a homomorphism in general on the whole space, on the whole group. Okay? Well, what did I miss here? This was not mu t, right? Yeah, this is not what I wanted to do. I wanted to do something else. Sorry. Okay. I wanted to do the sum.
Yes.
I wanted to first do the sum, right? First do the sum of t
To the J.
A1. Yeah, but why did I write it?
now we have one more term of J, U to J.
Something is wrong with my notes. Let's go back. No, let's keep what I wrote. Maybe it's good. Maybe it's good. So this is sum over x mu to the t of x V inner product C of X in the direction of C of X. This average does not go to 0.
What? No, but why?
So I just wrote down AT. AT is the average of mu Tx of Cx with itself acting on V. So this is what I wrote. I didn't do the sum with the big T. Okay? This is what I had before. And this average does not go to 0. Specifically, it means that this thing cannot go to 0. Right? Because if it did, sorry, I have to be careful what I'm saying now.
If you were 1/t.
Yeah. But even dividing by t, this whole thing, this is a convex combination. It's not going to 0, right? So this means that that the sum itself, right? I mean, if divided by t, it doesn't go to 0. The sum itself is basically of order t. Okay, but the sum itself is a convex combination of things, right? So let's be very precise. I was kind of like vague in the book. I kind of left this so it's clear, right? But what is it clear? So there exists an epsilon, which is strictly positive, and some t, which is also strictly positive, right? Such that, right? But some finite t, okay? Such that you don't need to take the limit, of course. I mean, go to the first non-zero element in this sequence, right? There is one. There are infinitely many non-zero. Go to the first one that is non-zero. So there is such thing, such that sum x mu t of x v cx cx is greater or equal than epsilon times t. Epsilon is going to be the limit, okay? Limiting value, or I mean, this was a vector. I mean, so yeah, so what I meant to say here is norm. Right? So this sequence of vectors with 1/t does not converge to 0. Therefore, there is an element for which the guy at place t in the sequence has norm bigger than epsilon. And this is what I wrote. This 1/t, just moved it outside. Okay? Okay? This is not just, I don't even need the epsilon, right? I mean, it's bigger than t. So, but this, of course, is a convex combination of vectors. So there has to be one. I mean, I can bound it above by the convex combination of the norms. So there has to be one. And this t is just some number now. There's no t going to infinity anymore, right?
Just non-zero.
Yeah, non-zero, because it definitely is non-zero, because when you plug in t equals 0, you get mu of 1, mu is delta 1, so you get c1, which is the 0. Okay? But even t equals 1 would probably already work, right? I mean, otherwise it would, but I don't care. T equal 1 min. It doesn't matter. Just to find a t. So there exists some x in yeah, what did I want? Okay, I have to be careful now. I have to be careful because I'm talking about, I want the thing to be I mean, it's obvious that it's an n when n has finite index, because you see, I mean, the walk comes back to n according to the density of time. So you could, I mean, if every time I was in n here, I would have a 0, then this sequence would have a lim inf, which is 0. Okay, and then it could not converge to. Okay, so
All the position at time t, so if we come back and come.
So let's write it this way. There exists an epsilon and a t0, okay, such that for every t after t0, this is bigger than epsilon t. Do you agree about that? I mean, the limit is going to be bigger in norm than epsilon. So I can just start from somewhere. Okay, now this is good, right? Specifically, right? For every t greater or equal than t0, right? The sum x mu t of x of this norm, okay, this guy comes out of the norm, becomes absolute value. And then I have the norm of c of x. All right, this is what the norm is. I just brought the norm inside the, made this side bigger, is bigger than epsilon t. Okay. But now this average for large t, I can take t for such that the probability that I'm in n is pretty good. Okay. So since g mod n is finite, yeah, so exercise there exists some delta such that the probability that xt is not in n decreases exponentially. Right? If you take a walk on a finite group, then there is an exponential on a finite group. There's exponential term. We already said you have a finite index sum. We already proved this. We already proved this, right? We said the return time has an exponential tail. The return time to
No, but this is like we said the return time of
sorry, the return time. So
yeah.
this is not what I meant. It's what I meant is that yeah.
No, but up to time t, like you cannot like at the time.
Yeah. Well, so what do I want to? I wanted to say that.
What we're trying to say right now that HV is not zero.
I just want to say that the sum of the x's in for a fixed for large enough t, the sum of the x's such that if you sum over x in n ut of x, you basically get a constant proportion. Okay, so let me give this as an exercise. Therefore, the probability that xt is in n, okay, this is going to converge. Okay, this is true for this is going to converge as t equals to infinity. In fact, it's going to converge to the index of it. Okay, to the 1 over the index of it. Okay, that's what it's going to converge. Basically, it starts becoming equally likely to be in any cosine.
So this is that the return time?
It's not the return time. This is the probability for the projected walk on the finite group to be at the origin. But it's true for any cosine. Just the stationary distribution is the uniform distribution. And you have to prove this. This is not a trivial exercise, but you can think about it. For us, it's easier and sufficient just to prove that this thing, so that the lim in for this is bigger than some. That's all. There's always a constant density of. Right? And what this means is that if I take this sum and I sum it over only over n, then I still have a positive density of the measure of things here, right? Which means that these guys have to be non-zero.
Is it true for any mu?
This is true for
any generating a measure mu. Sure.
Yeah, it's true for any symmetric generator. For any symmetric. Projective, just a Markov chain, symmetric Markov chain. Finite.
Okay. I don't.
Okay.
Stop at the.
So let me skip over the details of this also because I also forgot to kind of think of what is the correct way to do it without introducing some more background on the finite groups and the random walks. But all of these considerations lead to if the restriction of H to N was 0, okay. Remember, we said that the restriction of H to N is a homomorphism, but if it was 0, okay, then what we would get is that this lim inf would be 0. Why? Because at least you could imagine a positive density of the time I'm going to be spending inside N. And for N, I get here zeros, right? And so, and so I'm going to have a positive density of these T's, which are going to be giving me 0 in the sum. And so when I divide by T, this gives me something, so, subsequence which converges to 0. Okay? So the lim inf 1 over T ATV is going to be 0, which is a contradiction. It's only a subsequence which converges to 0, not just yeah, but I'm just saying the fact that this is 0 gives you a lim inf. The fact that we had their convergence tells you that it's impossible. Okay, so I'm going to leave the details out. If you want, we can come back to them, or maybe I put them on a new exercise sheet or something like that. Maybe it's a good guided exercise to do it. Okay. So this completes case. So again, case 2A was where I had the non-zero invariant vector, right? But G mod n was finite. Okay. So if the quotient is finite, then we found, what did we do? We found a finite index subgroup and a homomorphism from N into C. Right? It happened to be a homomorphism from N into C. Okay? So we found the finite index subgroup with a homomorphism into C. This is a algebraic consequence. Okay? So that we will keep in mind. I will summarize all the consequences soon. We're still left with case 2B, where the index is infinite. G mod n is infinite. In this case, again, G mod n, as I already said before, is isomorphic to G, which is sitting inside D by D unitary matrices over C. And G is infinite. Finitely generated, of course, because it's a projection of a finitely generated. And an infinite finitely generated subgroup of the unitary matrices, we have a lot of information about these things because of the unitarity, right? So this already goes back to theorems of Jordan, end of the 19th century. Okay, the structure here is so good that we really have a lot of information. It would be enough, in fact, by modern methods to get just a linear subgroup. But here it's unitary. We can even use like ancient methods from 100 years. Okay, so it's easier. And I could do it if I wanted to spend more time. It's not some algebra that you play because the unitary matrices, they form nice and clean. Get some stuff. Okay, so let me now wrap up Ozawa's theorem, show you the 3 things, and show you what happens in the polynomial growth. Okay, so change color just so that we understand that we're going into a new territory. Okay, I understand that I didn't do all complete details, and we can fill them in, but maybe they're less important for the picture. Okay, so the picture was, so the theorem Ozawa's theorem was the following. Okay, we needed an amenable group because we needed the harmonic cycle. Okay, so G is amenable, finitely generated, amenable, mu is inside SAG2. Okay, then one of the following, at least one of the following, holds. One, I don't remember how I wrote it last time. I'll write it in the order we did it this time. Okay. One, remember there exists a non-constant function in the Lipschitz harmonic functions. This is the HV that we had. Remember, it's the variance. Lipschitz harmonic functions for GU, such that if I take the variance for every x in G, right? If I take the variance of h of xt, in fact, this is uniformly over x, remember, because we had the convergence was uniform. Okay, so I can even write it this way. I can take the supremum over all x in G of the variance, and this is stronger than what I wrote last time. I divide the supremum by t, right? This is supremum taking over all x of a variance is bigger than just the variance of one, right? And even this supremum divided by t, this converges to 0 as t goes to infinity. Okay? It's a stronger statement, but it follows from what we did, because remember we wrote this variance as what? As just a AT inner product with something that has to do with x. But AT converged in norm, not in, right? So we can just take Cauchy-Schwarz to bound the AT divided by 2. Okay? So it doesn't care about the other vector, which is a very strong result. In fact, I was surprised by this first comments. Okay? 2 is case, what we said 2a. 2a was the case where n was finite index, right? And then we had, so there exists a finite index normal subgroup. It doesn't really matter, but we have a finite index normal subgroup and a non-trivial function, which we will still call h, okay, because it was the HV from before. H inside the homomorphisms from n into c. C is c plus, okay? Right? We found the homomorphism from n to c, not from g, but from n. So it's almost from g, if you want to think about it that way. Okay? And this gives a lot of information, as we will see. I will try to develop a bit. Well, I will summarize the algebra that goes into this. I mean, I will not do all of the details. That's more algebraic side. But you already have. So this is analytic information. It's a random walk information. Okay, it's analytic information. This is algebraic information. Everything here, there is no random walks and no nothing. There's just algebra in this statement. Right? You have a group. It has a normal subgroup, and it has a homomorphism. Everything is in the category of algebras. You don't need to know a word about probability in order to say, and mu doesn't appear in this number 2. Number 3 is also an algebraic statement, but this is a slightly more involved algebraic statement because it's a deeper fact about rings, maybe, or unitary matrices, right? Number 3 is that so G has an infinite, I'll write it this way, G has an infinite, this is important, projection. So this means that there is a subgroup of G that you divide by, and you get an infinite group. And that projection, which is a subgroup of U unitary matrices, D by D unitary matrices. Okay, so it has a projection. So anything I can say about projections of infinite unitary groups, okay, I can say about G, right? For example, I'm going to take those and find some. I'm going to reduce case 3 to case 2. Okay, so actually these are the same case. Okay, I'm going to say that everything which happens, I'm going to say that any infinite sub-exponential group here, okay, actually satisfies 2. But if you have a finite index subgroup here, which projects to which has a homomorphism, you can bring that homomorphism up to a finite index subgroup of G, right? Just because G is projected onto this, so you can just think it's inverse. Okay. So these two things are algebraic, and this is another.
What we're trying to show is if a group with polynomial growth, then
yeah, well, okay. Now let's see what we can do, how we can get Gromov's theorem from this. Okay, so now I'm going to list some facts, some stuff, try to make it clear what I'm not proving and what I am proving. Okay, the facts are not difficult. They're not difficult. And in fact, they are much stronger theorems. So everything I'm going to say that I'm not proving is going to be very well known and classical in group theory. So not even like something like and they also have elementary proofs because I did them in a much stricter case, certain stricter cases, so they have elementary proofs. To generalize to more cases, you might need more sophisticated metrics. Okay, so first of all, what we're trying to prove, goal, is Gromov's theorem, which is every polynomial growth group, so this means finitely generated group with polynomial growth, is virtually nil. Has a nilpotent subgroup of finite index. Okay, those are the only examples known, and Gromov showed that's it's a characterization. Okay, so you go from geometric information to algebraic information. The other direction was already known from the 60s by Wolf.
right? What? So we proved the Ozawa theorem.
We proved Ozawa's theorem. Exactly, this was case 1, case 2a, case 2b. It's exactly what we got, right? The n was the kernel of the action. If it was finite index, we got the non-trivial homomorphism. If it was infinite index, just take the projection into the unitary. Right? This is why this becomes infinite.
Yeah.
2 is also 3 because this quotient is a unitary but it's a finite one, so that doesn't really help. Okay, now, first reduction. So, theorem. This is a conditional statement. So it's going to tell me what do I need to prove in order to prove Gromov's theorem. Okay, if so this is let's call this the reduction theorem, so we can come back to it. Reduction theorem is if every group of polynomial growth is virtually indicable, I will say what that is, then Gromov's theorem holds. I have to prove, first of all, this statement, conditional statement, right? And then I have to prove that every group of polynomial growth is virtually indicable. What is virtually indicable? Definition. Yes, G is virtually indicable. Just a sophisticated word to say something simple. G is virtually indicable if there exists, so virtually is always finite index subgroup, right? So I could just define indicable, and then you have a finite index subgroup, which is indicable, but let's, G is virtually indicable. If there exists a finite index subgroup, such that there exists a non-zero homomorphism from N into, let me write C. Now let me explain why this is important. Okay, let me explain why this is important. And in fact, kind of prove the reduction while I'm explaining why this is. Why do I even want to look at this? Why did Gromov even think that this is what he needed to do in order to prove it? Okay, so a little bit of algebra. Okay. So first, if n, let's write if n is indicable. So what does indicable mean? Indicable just means that I just have this homomorphism already on n. I don't need a finite index. Because virtually just means go do something on a finite index level, right? N is indicable. So
n is just a subgroup or no?
Well, it's you can always take it to be a normal subgroup. So if you have a finite index subgroup and you intersect all its conjugates, then you still have a finite index normal subgroup. So you could always assume it's a normal subgroup. Okay, just restrict your homomorphism to that point. It cannot become trivial on a finite index subgroup. Okay, so if n is indicable and we have a non-zero homomorphism from n to c, okay, then an homomorphism inside an abelian group, inside C, must be either span and n is finitely generated. Okay, so everything is always finitely generated. Finite index of a finitely generated group is finite. Okay, so if I talk about growth, then I'm talking about finitely generated. So then h of n, what is h of n? Right? This is isomorphic to n mod the kernel of h, right? That's first isomorphism theorem, right? But, so this is a projection of a finitely generated group. So this is a finitely generated group, okay? Is a finitely generated group. So this is a finitely generated subgroup of C plus, right?
You start with a minimum group to get and project to get a minimum group. Oh, you take the projection of the partner.
I think so. The other thing is not true. Projection of a non-amenable group is not necessarily non-amenable. Free group, non-amenable, projects onto Z. Karen took the extreme case. That's a project of a finite groups are finite groups are. Okay, so so we have a subgroup of C plus, right? If h of n was finite, just as a set, we have a finite subgroup of C plus. Finite subgroup of C plus is finite. Finite, right? Because okay. You know what? Let's do it differently. So if h of n, so h of n is isomorphic. It's a finitely generated abelian group, right? So it's isomorphic to some ZD times F, where F is finite. Any finitely generated amenable group, abelian group, is just ZD times some finite portion. I'm not going to prove this. This is a fundamental theorem. You can prove it using linear algebra. Best thing I know is to use linear algebra. Because this has a very, very nice structure as a subspace of Q to the D. Okay, there's a proof in the fundamental. So this fundamental theorem of abelian groups. I mean, basically, what you do is you look at this thing, you look at the generators, okay, and you take generators from this set, and then you say which of the generators are infinite order and which are finite order. If they're finite order, they go into this thing. That's fine. You have an abelian group with finite order elements, right? It's always finite. And the infinite order ones go into this thing, and it could be maybe that they kind of have, they're not linearly independent, right? See where the linear algebra comes in, but you can reduce them to a linear independent thing, and so they span something which is going to be isomorphic to ZD, because they're generated integer multiples, right? What are elements? I didn't say. I just said any finitely generated group.
Oh, okay.
Any finitely generated group looks like this. And I basically told you now how to prove it, like, using the algebra. But no torsion elements. C. Additive C. Additive C. Do not add the complex number with itself, right? Enough times to get 0. You can multiply. Right? This is additive C. Okay. So what does this mean? So this means that H of n is just a trivial group, right? If and only if H is identically 0. Sorry, that's the right. If and only if H of n is finite. I cannot have a finite abelian subgroup of C unless it's a trivial, right? And so, since we assumed that H is not a 0 function, so this is not the case, H of n is infinite. Look, and in fact, it's Z to the D because there are no torsion elements. Or some D. Some D. I don't know what it is.
Maybe the growth rate.
Well, of course, if you know the growth rate of the image of H of n, then I know the growth rate of H of D, so I have the same growth rate. Okay? Yes. But I mean, there is a way of seeing D in a group, but I mean, now it doesn't come from something in N. Depends on the kernel. Okay, but specifically, what I wanted for all of this picture, I told you I'm doing 3 gives 2, right? 3 gives 2. So, specifically, you know, there is a homomorphism from ZD to Z, right? Project on one of the coordinates, first coordinates. There's always a homomorphism onto Z. Maybe not onto Z squared, because maybe D is equal to 1. Oh, should have said D here is this one. Okay? But specifically, so there exists a different homomorphism that I can take from the original group N into Z plus, Z plus, okay, that is surjective. But I'm just saying, H is a homomorphism from N onto H of N, which is isomorphic to ZD. Project onto the first coordinate, concatenate all the homomorphisms, you get the surjective homomorphism.
For that, we just need. Don't we need just an element with a order? For that?
Not every time you have an element with infinite order, does the map taking you to that thing give you a homomorphism?
Sorry.
Okay.
Yeah.
So, but what we just said is first of all that indicable and surjective homomorphism. So indicable, or let's say finitely generated indicable, is equivalent to exist surjective homomorphism onto Z. Okay, that's one thing. This is, so let me write G is finitely generated indicable if and only if surjective homomorphism to Z. This is if and only if you have some G mod N. This is a different N, right? G mod N, or let me write G mod Q. Okay, is isomorphic to Z. Right? That's easy. I mean, K is the kernel of the surjective homomorphism, right? And this is if and only if Okay, and here I'm going to sweep the details under the carpet. Okay, this is if and only if for every G in G there exists ZG in Z, just unique. And we'll see in a second why they're unique. ZG in Z and KG in my subgroup K. Okay, such that G is equal to okay, sorry, I said unique, there exists unique KG, and there exists some A in G. So this comes before. There exists some A in G, such that for every element, there is a unique Z and a unique K. And the A is not unique. A can, there's a choice for A. Once you choose A, you get uniqueness for Z and K. The G is written this way. G is written K to the KG times A to the power ZG. That's what every element can be uniquely written in this form. Okay? In such a group, this is exactly the definition of a semi-direct product. Okay? So if and only if G is Z acting on K, this acts via some automorphism. I'm not explaining exactly what this construction is. This construction is basically this. It's basically, if you write this, this is the same. You can split your group into a K part into a Z part. Okay, and multiplication here is obvious how you multiply. Multiply, K is a normal subgroup. So if I multiply two elements, what I get, let me just write that down just to this is the end. So if I multiply two elements of this form, if I have K A to the Z times M A to the W, right? So these are Z elements, this is A, and these are elements from K. Then how do I multiply these? I want to bring it into the unique form. Well, it's easy. All I need to do is I write K A to the Z, M A to the minus Z. K is a normal subgroup, so all of this thing is in K. And then I have to pay back with a Z for this thing, so I get this. And because of the uniqueness, you see, this is the unique new element, and this is the unique new K element. So you exactly understand how to multiply things. Okay? And this is exactly the structure of a semi-direct product. Every semi-direct product in Z looks like this. Okay, so these are all equated in sync. You could imagine why this gives you, why this is useful. This is useful because it reduces studying G to studying K. And K is slightly smaller. Yes, so you can define Z acting on K, and if you're going in this direction, Z acting on K so you need to define what one does, and one acts by conjugation with A. It's your fixed element. It's not unique. There could be many different A's do the same. They do different things, but they give this isomorphic. So if you know what a semi-direct product is, that's the way to go. In the other direction, if you know that G is Z acting on K, then you have to take the generators for K, you have to take the generators for Z, you have to understand why K is found in J, and then or actually you don't need to take the generators, right? But I mean, you take some element that is mapped to the generator to one here. I mean, elements of this thing are pairs in a sense. You take some element that's mapped from G to one of Z, which is not the identity element, identity is 0, comma K, to comma identity in K, and that element will be your A. And once you fix that, there could be many of them that will be this. But once you fix that, then you exactly get this decomposition. Okay, so this kind of explains why we want to do these things. We want to do these things because we can move from G to a smaller subgroup. Okay. And next week I will explain how this helps with problems. explain exactly the steps.